Okay, so we made it. So thank you very much for being here. I know it's summer, and thank you for the invitation, Yorgo. Good to see all of you, and good to see my friend David too. Okay, so I will talk about how you can do sensor and actuator placement for resiliency in complex systems. So let's see. Okay, let me see if I can. Okay, yeah, I can move it. So our lab is called Intensive Physical Systems. So what we do is, of course, CPS are highly complex interconnected systems. It combines physical, computational, communication components, and then the applications are everywhere. So of course, the time that you make it more complex, this increases the uncertainty across all layers. And then, of course, we have more data, so we can use more data to do what we know as controls people. And so the first part of the talk will be about something we call as data-driven actuator selection. Okay, so what is an actuator? So I'm sure you have opened some toys, so you know these little toys. Of course, the actuators are not that small, but you all remember this if you opened any toys when you were young, and then you had some RC games, and then you see these little actuators. So in control terms, though, what you mean is you pick this column of the B matrix. Every column of the B matrix is actually implements a control info, okay? So this is what it is. So why it is important? Because, of course, by picking the appropriate actuators, you can increase controllability, you can be smarter in handling faults and failures, and you can improve energy efficiency depending on the task you're doing, okay? So, of course, up to now, all the actuator selection algorithms, they're model dependent. So this means, for example, for linear systems, when you go to linear systems 101, you remember X dot equals A plus BU. So you need A and B, right? We don't necessarily know A and B. So we want to do displacement by using ideas from reinforcement learning. And also, even if you know the model, these problems are NP hard because it explodes with the dimensions. You'll see what I mean. So again, since we work on cyber-physical systems, these are large-scale systems where the system is not available, or even if you have something, it's inaccurate. Or, for example, you fly a plane, right? So if you have computed the optimal controller for that plane, let's say a Riccati equation. So this is not optimal because the plane burns fuel, so the mass decreases, so it's not optimal anymore. So many things can happen, and then you're sacrificing optimality. So this is what I mean there by the system may change over time. Okay, so solution, data-driven actuator selection. So let's see. So let's go again to our 101 linear system class. So we have X dot equals A plus BU. You will see that A and B will be unknown, but for now, let's give a system so we start slowly building on that. So X is the state, U is the control, A and B are the plan, and the input dynamics matrices. Okay, so remember that every column in B, okay, is an actuator. Remember before, these little toys are actuators, so every column in B is an actuator. So for every B, what we will have is that we will have a fixed part of the B matrix, and then we have a choosable part of the B matrix, okay? So you will assume that the B0 that you see over there is the fixed part. What you mean by fixed is the actuators already incorporated into the system, and then mathcal B are the actuators that need to be selected or placed, okay? And then you will see that we will do that with data-driven techniques. Okay, this is what I just said. So, of course, I didn't even tell you what choose means here, so let's see what it means. Again, I have a bunch of actuators. Again, remember that in a cyber-physical system, you have redundancy in actuators and sensors, as you will see. So I have a pool of available actuators, so they're in this set, and then I have to pick the best of them, which is K, okay? So I have to pick the K best of them and put them into the system, okay? So Of course, I told you one of the things that we want for actuator placement is we want to improve controllability. So we have to select the best of them such that we maximize controllability, okay? Which I haven't told you yet what this F mathcal B is, but of course I have to pick the K best of them, okay? So let's say for now I want to maximize controllability given that I have K actuators. Okay, so after I have them right, I place them, and then the system operates. Okay, so how we can quantify this controllability of actuators? So in other words, how I can find this F of mathcal B? Okay, so pretty straightforward again from our 101 linear system theory. Okay, so what I want to do is I want to solve this minimum energy problem where it is given by this. I mean, I'm sure you have seen it in the past. Okay, so but I want you to remember that the more controllable systems, they have better optimal values, right? Because you do minimization, right? So every time you want to improve on something, you want to improve on controllability. So this will have a better optimal value. I mean, by better is because in controls we're pessimists, right? So since we're pessimists, we want to minimize, although our economist friends are more optimists, they want to make money, so they maximize. Okay. So again, this is very easy to solve. I'm sure you have seen it in the past. Okay, so the optimal value is given by this guy over here in blue, where QTF is given by this. Again, this is just the controls 101. Okay, so this is the Gramian. Of course, this quantifies how good my B matrix is. Okay. Okay, so of course, as you can see, this Q over there means that since I want to improve controllability, the bigger the Q it is, better controllability it is, right? So small Q is worse, right? So of course, remember that one of my things here to do is I want to pick this F of mathcal B, okay? So one can choose the trace of this Q, okay? Again, nothing too fancy. Okay, so what we have here is, again, I want to maximize that such that given picking the best K actuators, again, the TF that you see over there is free. Of course, if I expand my horizon to infinity, then I don't have I have an algebraic equation over here, right? So there's no integration involved, okay? Again, I'm sure you know all these things from before. One caveat here is that, remember I do actuator placement, so A must be Hurwitz, but of course, if I don't assume that A is Hurwitz, I can do this trick, right, where I can move the eigenvalues on the left, right? I'm sure you have seen that in the past as well. Okay, so remember that, so before I have the trace QTF, right? Now TF is to infinity, so I just have Q there. So of course, this Q comes from this equation over there, that in order for me to solve it, I require A, right? I don't want A anywhere. I want it to be model free. So I'm not satisfied, so I have to find other tricks. Okay, so what we have to do is we have to find a way to make this Lyapunov equation, to write it in a way that I can solve it with reinforcement learning. Okay. Okay, so but there is one problem, because up to now, what we have done in the past is that we can solve Lyapunov equations, but they have the transposes on the other side. Okay, so the red that you see there, for example, if you have a Lyapunov equation, you say transpose P plus PA, right? Equals minus Q. But now you see that transposes appear in the wrong places. Okay, so keep that in mind, and then you'll see how we can solve this one as well. So this is our first theorem here. Okay, so if we have the model known, right? So this is a theorem. So you find your P and you solve it, okay, and then you maximize eventually your F of mathcal B. Okay. Again, here you know the model. I just put it here for information. You'll see how we can do it with learning in a bit. Okay. Let's see. Remember that the Lyapunov, the good Lyapunov, I will say, and the bad Lyapunov. So the good Lyapunov is A transpose P plus PA. So this actually looks like almost a derivative of X, right? So let's see what we can do. So now let's get into the learning part. So the P over there, you can think is the solution to the Lyapunov equation, okay? So, and then remember that this A transpose P plus PA is almost the derivative of X. So what I can do is I can pick this part, which is a Kronecker product of X, and then X T minus T, Kronecker X T minus T. I can vectorize it, and I can use this as a basis function, okay? So again, if you write down this equation that you see on top, which is this one here, it's nothing but this version here. But what I have done is I have vectorized P, and then wherever I was seeing X, I was using it as a basis, okay? It looks tricky, but it's not. It's very easy to be right. So now you see that phi of transpose T can serve as a basis. The vectorized, which is a half vectorization of P gamma because it's symmetric, so can serve as an unknown basis function, an unknown weight vector, okay? And then everything else is known. So I can measure X, okay? So the only unknown here is the P, okay? So, of course, we can solve it offline. So of course, the easiest way, you can do least squares, right? You can do least squares with respect to the vacates P gamma, okay? Or you can use other techniques, so recursive least squares. So again, with least squares, you measure, you have points, you create points, and then you solve the least squares, or you have trajectories, you do recursive least squares, or you can do gradient descent or anything you want, okay? You pick your favorite algorithm and you solve it. Of course, if you do least squares, you have offline, right? If you do gradient descent, then you can do online, okay? So, so what we will do here is, remember that in order for me to guarantee solution, this has to be 0, right? So, but it's not always 0, okay? So this is an error, okay? So if you want to pick a gradient descent, you pick an error, and then you make it quadratic, right? And then you pick the weights, which is the half vectorize of P gamma, you pick them with gradient descent, okay? So it's pretty straightforward. So this is my error, okay? Which is what you saw me 0 before. And then I pick my gradient descent, and then you see the difference part is this I normalized over here, but everything else comes from the gradient descent, okay? So here, E is what you see, and phi are the basis functions, which are the X Kronecker X, X T minus T Kronecker X T minus T, okay? Which is the data I can measure, which is a measure of the full state here. And then, of course, the sigma is the Salenic rate, okay? So pretty straightforward again. So this way I can learn my P, okay? That has to do with my actuator placement. And of course, as a controls person, we always prove that everything goes well. Okay, so then again, this is the Frobenius norm, does not increase, and everything goes to 0. In other words, I identify the optimal P. Okay, so there is something that in adaptive control is called presence of excitation. So this means that you add some noise to your control input to excite your system such that you can move around and explore the state space. Okay, so in learning, this is exploitation exploration. Okay. In control terms, the P is just given by this interval, okay? So of course, you can see that the P, excitation, is for the future, T plus TF, okay? So rate of excitation in adaptive control is known that you have to guarantee that your system is excited over the future horizon, okay? You can't guarantee it always, but people have worked by relaxing this condition by something called concurrent learning, where instead of saying, okay, in the future, I will guarantee that my system is excited, I use some data from before, and then you can, it's like replay, experience replay. and then I can guarantee that, okay, I have this data, and then I don't have to guarantee that in the future I need my signals to be excited, okay? But yeah, there are many variants of this one. Okay, so what happens now is I wait until my peak hat converges, okay? And then I select the best actuators, and I can do that online or offline. You'll see in a bit, okay? But of course, the most interesting thing is when you adjust your actuators online. That's what I will talk about. So at any time instant t, tj that you see over there, okay? I pick the set vj, okay, by solving this maximization here, okay? So tj, and then peak hat, tj, are the estimated weights at instant tj, okay? So this is a tj are the times that I have to select my actuators, okay? And then in order for me to do that, I have to solve this optimization. And of course, as you remember from before, A doesn't appear anywhere, okay? So this is the learning algorithm. Again, what we do, we find the p hat, I sort the values, because remember I wanted the k best ones, okay? And then I put them into my B matrix. The bj, j means that because I update every tj, okay? Okay, so of course, as I said, we're controls people, we like the theorems, okay? So if I keep updating that one, I can eventually find the optimal actuator placement in finite time, given, of course, I have some condition that is from before exploration exploitation, and I can do that in finite time. Okay, let's see how this kind of work. So again, as I said, since I'm an aerospace engineer, I also have to put something about the plane. So this is it's a benchmark aircraft by Saab. Some people try fault-tolerant algorithms or redundancy algorithms in this aircraft. So this system has this A matrix, which of course will be a known for us. And I have to pick 4 actuators to place, and the other are some parameters. I have to place my actuators every 10J, okay? And let's say that I knew the system from before, and I want to solve it offline. So if I knew everything about the system, then the optimal solution will have been 3, 4, 5, and 6, okay? So let's see if our learning algorithm will eventually converge to 3, 4, 5, and 6, okay? So first on the left, you see the convergence of the P gamma, okay? So you see the convergence on that one. Of course, everything goes to 0, so we're optimal. And here, what you see is, so black is when the actuator was not picked, and then green is when it's picked, okay? So here's the TJ terms, okay? So you see that I converge to 3, 4, 5, and 6, okay? I solved the problem online without A, and I converged to that one solution if I knew the model, and I can solve it offline, okay? So what we did up to now is in my group also we do superficial attacks. Okay, so let's say that you have a bad player into your system that wants to ruin your controllability. Okay, so let's see what happens. Instead of having the U transpose RU that you had before, you have an extra player into the system, which is this A, which is a bad player into the system, which is trying to ruin your controllability, okay? So this is eventually a zero-sum game, or for the controls people, H infinity control, or whatever you want to call it, okay? So you have a minimizer, U, and you have a maximizer, A, okay? And then instead of solving a Lyapunov equation, you solve this something that is like a gain Lyapunov equation that you will see in a bit. So yeah, the same thing with before, but instead of having the Gramian with the optimal Gramian, now you have something that we call the game-based controllability Gramian, which is given by this guy over here. Okay, so again, what you do, you just pick this Q, you put it back into your f of b, okay, and you do the same things. Okay. So yeah, the rest is the same. So again, what we did up to now we developed the model-free actuator selection algorithm. We selected actuators that quantify controllability and attack resilience. And of course, we always prove equivalence between the model-free and model-based. So there was some things that we didn't like. Oops. So the controllability was measured on average, not across closed-loop trajectories. So what we can do here is we can also do controllability across closed-loop trajectories. If we do controllability across closed-loop trajectories, we don't have the actuator placement problem, but we have the control allocation problem, okay? So again, let's go back to our favorite system dynamics. Again, your X is the state, your V is, we don't do control synthesis here, remember? So V is a pre-specified control input, and A and G are the unknown planet input matrices, okay? Okay, so of course, for those of you who wants to see it visually, I can map any actuator to any controls by doing this manipulation, right? Pretty straightforward. Remember that the B's columns comprise the actuators, and the U is the actuator commands. And of course, the V, as you remember, is the pre-specified control input, okay? But I can always map actuators to controls. Okay. Again, remember that our system is actuator redundant. Okay, we had this before too. Okay. Of course, again, I want you now to interpret it with respect to V. So any control V with appropriate choice of U will define actuator redundancy. Okay. So since we do that over trajectories, as I told you, this is a well-known problem, which is an allocation problem. Okay. So actually, this allocation problem is pretty popular nowadays because when you want to control eVTOLs, okay, and then some of the rotors goes off, you want to allocate your control to the other rotors and still fly the aircraft. Okay, so let's start slowly, okay? So if you have allocation problem, this is actually solving this minimum energy problem, okay? Again, remember these over trajectories. So of course, you can solve it pretty easy because this has a closed form solution, okay? And the optimal solution U star is this, and the optimal cost is this, okay? Pretty straightforward. You can do that probably in your optimization 101. But there's something here that's very important for a controls engineer once you want to optimize even more. So you can see that the optimal cost involves this PW inverse B transpose, okay? Remember the W is a user-defined matrix over there, okay? And the B are the columns, or has columns as actuators, okay? So if I optimize a further B, I can further optimize this optimal cost that you see over there, right? Again, straightforward. So let's see how we can actually pick our actuators to do optimal control allocation. Okay. Again, pretty similar with before. We separate B in B1 and B2. So B1 has K1 components and B2 has K2 components. And again, same with before, I have my fixed part and a choosable part. Okay, but now I want to do control allocation. Okay, so I only have control of the B2. So what I will do is I will pick B2 such that the optimal cost that you saw before in the previous slide, which involves the BW inverse B, right, is minimized. So what I will do is I have to try to pick something that looks like before, okay? But of course, now I have the minimization problem. I have to pick a K2, okay, because I have K2 choosable parts, and then eventually put them into the system. Again, this F of B, before, remember, it was controllability. I want to maximize controllability. Now I want to minimize energy, okay? Okay, again, there's just redundancy. Don't worry about that one. So let's do the first case, okay? The first case is the agnostic actuator selection. Remember again, our optimal energy is given by this guy over there. And what I told you is that the V is a pre-specified control input, but if V is not fixed or known beforehand, one cannot directly find this one, right? Okay, so let's see what we can do. We will optimize on average, okay? And then by optimizing on average, you can choose F to be the trace of this guy over there. Okay, BW B transpose inverse. Okay. So, and the case two is, of course, when I know V. Okay, and so suppose that V is given by KXT, such that your A plus GK is orbits. Okay, and then the initial distribution condition is given by this guy over there. Okay, so then what I can do is I can pick F to be that. Okay, so again, so now this one is because I know V, I can pick it as KX, right? And then you see that I have eventually this infinite horizon F of P. Okay. So now I want to minimize that guy over here. Okay, and then my freedom is this BW inverse P transpose. Okay, so again, in order for me to use learning, I have to somehow write all these guys in a Lyapunov equation. Okay, so it seems that when I want to solve that, then it relaxes to two equations that they're coupled. Okay. And they look like that. But also, I want you to pay attention that this guy over here can be written as the trace QR or the trace PV. Okay. So there are problems with this one. So the first one, the trace the PV is inefficient because I have to solve the Lyapunov equations for all points into to the power of mathcal S. While if I do QR, then I solve only one Lyapunov equation for Q. Okay. So of course I will pick the second one, right? Okay. I can pick the second one, but can I do it in a model-free way, right? Okay. So the cost function is, again, I picked it and then subject to these equations that you see over there. Okay. So again, I want to minimize this trace given that I have these matrix equations that you see below. Again, remember that the only bad things that I don't want to have anywhere are the A and G, okay? Remember that my system was x dot equals AX plus GV, okay? And B is the choosable part, so of course I know it, right? It has a fixed part and a choosable part, of course I know. I have to do model-free the second equation that you see downstairs. Okay. So again, this is just what I just said. So I want to find this Lyapunov equation and solve it model-free. But we have the problem that I told you before, okay? So the transpose is appearing in the wrong side, okay? So this is not actually a Lyapunov equation. It's we'll call it a dual Lyapunov equation. So I have to find a way, because I want to do it in learning, and in learning, I know how to solve Lyapunov equations that they have the transpose is A transpose Q plus Q A plus blah, blah, blah. So I want to make it look like that. So I will do the tricks that I say that every control engineer needs to know. It has to multiply, post and pre-multiply, as well as at zero. This is the only things that you need to know in controls, okay? So what I do here is I multiply left and right by Q inverse, okay? Of course, by the theorem, Q is non-singular, I can do that, okay? So if I do that, then you see that my transpose is appearing in the right side, okay? So now I can solve this, right? I can just put it in any algorithm that we have done in the past, and I can solve it model-free, okay? So you will see how we can do that. Again, I can use Polish iteration, bad iteration, you pick it, okay? But remember, because I pre and post multiply and I flipped the transposes, okay? So when the transposes appear at the correct place, this finds the stabilizing solution, right? But because the transposes appear in the wrong place, then this is an anti-stabilizing solution. So I don't need my A plus GK plus Y to be Horvitz, but I need my -1 to be Horvitz, because this is an anti-stabilizing solution because of the fact that the transposes appear in the wrong side. Again, we prove the equivalences. Of course, also, you don't have a constant term. So many differences than before, but this is before because this is the anti-stabilizing solution. Okay, so now we can do learning. And as I did before, whatever I know, and then I can measure, I will put it in a basis, which now is the psi. Whatever I don't know, I will put it in the vectorized form, in the unknown weight vector, okay? And then I can define eventually an error, and then I can solve it with least squares, recursive least squares, or you pick it, okay? Again, the idea is simple. Whatever you know, you put it into, whatever you can measure, you put it into the basis. Whatever you don't know, you put in a weight, and then eventually you solve it as, with your favorite algorithm. And then if you want to see exactly what are all these sci-fi Greek alphabet stuff, they're given by distance. But they're pretty similar with before, okay? There are things I can measure and things that I don't know. And then I just put them and make these Greek letters to confuse people when they do my papers. Okay. Of course, this matrix is singular, so that's why we can solve it. There's just some dimension stuff that we have to make sure exists for this to be solved. Okay. Again, I can solve this pretty easy, as I said, and I can estimate Q inverse in real time by using this little algorithm that you see over here. But again, the idea here is, again, I do everything for the other anti-stabilizing one. That's why you see the minus over there. And then I compute, and when I'm satisfied with how far my two iterations are, so then I can stop the algorithm. Okay. Again, this is Poly's iteration. For those of you who don't know, I need to start with a stabilizing solution. Stabilizing is like stabilizing control that also gives me a finite cost. And then I iterate between policy evaluation and policy improvement. If I do value iteration, I start with any policy. And again, I iterate between the policy iteration and policy improvement, okay? But of course, policy iteration is faster than value iteration, but value iteration doesn't require to start with a stabilizing solution. And again, as I said, everything we do will prove that it is it's going well. Okay, so now, as I said, this is very useful for eVTOLs. Okay, so we had a project with, we still have a project with NASA. So we want to stabilize extinction when something bad happens. So I have 9 states, okay, and I have 5 high-level control inputs. And this S that you see there, then all the available actuators that if something happens, I want to allocate them and do optimal allocation. The initial actuator set that already incorporated into the system, there is 1, 2, 3, 13, and 14. This assigns the order of this, right? So 1, 2, 3, 13, and 14. Okay. And now what I have to do is I have to augment this B1 with B2. Okay. So I have to incorporate 6 more actuators. Okay. And do my optimal control allocation. So again, what I eventually want to do, I want to minimize this trace. Okay. These are just some constants we picked over there, some exploration noise. So what you see on the left is the norm for state, the norm of the V, and here is the convergence of the Q inverse to the optimal solution. So everything goes well. And the result is 2, 3, 4, 6, 7, 11. Okay. So this is actually, if you do it model free or model based, so you will get the same solution. And here we didn't require any information about A and G. So I have a little bit more. So this just concludes this part. So again, what we did is we combined, we used an actuator selection algorithm for optimal control allocation. We did a model free, and of course we proved small disturbance input to state stability, robust to input noise. Okay. Okay, so now we will go to actually a harder problem. It's how you place sensors. Okay, so or how you select sensors. Okay, so and of course I want to do that in discrete time. So before it was continuous time, now I went with discrete time. So let's see. Okay, I have this system. Okay, and so now you see I have an output. Okay, so of course, if you do sensor placement or sensor, or you do sensor selection, you have this Y's, right? And A, B, and C are completely unknown. Okay, I don't want to identify them, but I want my algorithm to be model free, not depend on A, B, and C. And so now, instead of having the B's, which are the columns, each row of the C is a sensor, right? Again, same things with before, but now you do it from the perspective of sensors, okay? And the sensors appear in the Y that you see over there. Again, same with before, I have to pick P prime, which is less than P, which is the rows of C. And this is what I have to do for the sensor selection. Okay. Again, choosing sensors, choosing rows, right? Nothing too fancy. Okay, so since selection, we'll come back to what we know are selection metrics, okay, which is actually pretty interesting. So what you have to do is you pick 0 and 1s on this selection matrix, and then you pick the appropriate parts of the C, okay? So in other words, you flip 0 and 1s, and then you occupy the appropriate parts of C, and then you have this C tilted, okay? But you have to find a smart way to find the selection matrix, okay? Of course, I cannot start something without the classical observability stuff, so I have to assume that a sensor set is already involved, and then I'm already observable, okay? Before I start, right? Of course, I mean, you cannot do anything if you're not observable. Okay, so now, how do you define which are the best sensors? Of course, before we defined which are the best actuators, we defined them based on controllability. So straightforward, right? What it will be? Something that will penalize how strong the signals are. Okay, so in other words, how this H2 norm. So I want to maximize how they get what sensor gives me the most reliable and the stronger data for me to do my control. Okay, so and this is just maximization of this H2 norm. Okay, it's pretty straightforward, right? You see just maximization of the Y square. Okay, before I had U square in a vague sense, which was controllability. Now you can think that it is, I want to maximize some form of observability, but not really, because this is, you want to maximize the strength of the signals. So again, if you do some easy calculations, you will find out that this expected value is actually equal to the trace of CWCC transpose, which is equal to the B transpose W0B. And somebody can say where you can find WC, W0, you can find them from these two equations over there, okay? So if you solve WC, you put it in the first, and W0, you put on the second, okay? So this is what I just said, okay? So remember that everywhere you see C, you have to multiply it with a selection matrix, okay? And I want to do that only with input-output data, okay? Because if you place the sensors, you cannot measure the state, okay? You can measure only input-output data. And I measure previous data. So I form my previous history of data, input-output data, and then eventually I can pick what I want. So this is actually a problem statement. Again, what I pick the CWCC, I multiply it with my selection matrix, and I want to maximize that, okay? Okay, this is what I just said. So, and the idea behind that is very easy to understand. So I have a state. I can write every state as a sequence of previous inputs and previous outputs by writing with respect to controllability, observability, as well as the top list metrics. Okay. So, and by that, so you see, this is the controllability, observability. This is the top list metrics. Okay. The Z is the history that goes from T-1 to T-n, and same for Y. I stack them together, and every X is given by these variables. Okay. Again, this is a way to write every state with respect to previous input, previous output data. Okay. So keep this in mind, and let's see how we can use input-output reinforcement learning to learn and do sensor selection in real time by using input-output data. Okay, again, and what I told you before, like you seen before, what I know and what I don't know. What I know and what I can measure, I put it into my basis function. What I cannot measure, or what I don't know, I put it into the unknown weights. Okay, and what you see, the y gamma is the output of the sensors to be evaluated, and then of course we need some ranks to guarantee that everything goes well. So this is the cost, and let's see how this can be put together. Actually, let me put the algorithm here. So this is our algorithm, okay? And this uses input-output data. I know, sorry, I put some equations there. But what I do, I gather input-output data. I evaluate my cost, okay? Then I rank my gammas, which are my sensors, and I pick the best of them, okay? And I put them into my system. And then this requires only input-output data and can be found the sensors in polynomial. Again, this is what I just said. Of course, in discrete time, you can use this idea as well for input-output data to place the actuators, or you can extend that to other observability metrics, which are finite horizon or volumetric observability metrics. We have done both of them. Okay, so let's see how this can work. So imagine we have this IEEE 39 bus system, which has the order of the system is 20. Everything else is there. But of course, this is continuous time. Of course, I've had to discretize it. And I don't know any information about A, B, and C. Okay? Okay. So remember that in the beginning, I will start with an initial set of sensors, which in this case will be 1, 3, 4, 6, and 8. And I have to augment it with 7 more out of the ones that you see over there. Okay? This is just what we have picked for a volumetric cost. So what you see on the left, this is the estimated cost for all possible sensor sets. And then on the right is this measurement, which of course you can see it's close to it's 0. And the greedy algorithm found this is the initial one, but then incorporated 2, 5, 7, 9, 10, 13, and 18, which are the optimal ones. And right on time. So again, what we did here was we utilized reinforcement learning to solve different problems like placement actuators and placement of sensors. We also did optimal control allocation. And I wanted to show how important it is that some problems that they're almost impossible to solve with model-based techniques like actuator placement, you can solve them efficiently with reinforcement learning. We have tried large-scale systems. We have tried order of 10, order of n equals to 100 in our journal paper. And with that, I would like to thank you for being here. And by the way, Philippos actually works now with Ufuk and David at UT Austin. So yeah, so he was the one responsible for most of this work. So I'm happy to take any questions.